Okay. Thank you. Let's see. I'd like to thank the organizers for asking me. I'm part of an experiment that's called the First Proof Project, which they thought there might be some interest in, therefore my completely uneducated views about artificial intelligence. The truth, I'm not a neuroscientist and I don't work in AI professionally, so all that I'll do is I'll do what anyone else would do if they were asked to spend an hour to let people set up for Kiddush. So, no, it's also great to be part of honoring Alex Lubotzky. So the first thing that one big influence, I heard him give the Shanks lectures at Vanderbilt, and he came, he was wearing a jacket, and he said, this shows your respect for the audience, but after you show the respect, you can take it off. And I appreciate Alex for showing the way. No, Alex, the theme is sort of natural intelligence and artificial intelligence, and one of the things that's really great about Alex is that he gets people to be more intelligent than they normally would be. No, I mean, he's a great collaborator. He pushes people to think about questions that they're uncomfortable about. And in fact, last summer, he had invited me to Oxford to give a talk about AI for a meeting about AI and math. And that one was actually a mathematical talk. I discussed some issues related to how evolutionary theory is different for humans that evolve based on DNA as opposed to AIs that are evolving based on various kinds of network architectures. And I think that, and trying to understand scientifically some of the questions that I'll talk about now probably do involve understanding mathematics that we don't even understand qualitatively, but we need to understand them quantitatively to try to come to terms with these phenomena. So therefore, like I said, all that I'll be able to do is pontificate a little bit. But the point is that a lot of us feel uncomfortable with AI. Partially we think of ourselves as Homo sapiens, right? The humans that think, right? That's sort of the defining nature of our species. But going back to Chumash.
You don't prefer full screen.
Well, I don't know that it will work so well.
Control L.
Control L.
Yep. No.
Oh, that's better? Okay.
For us, I think it's better.
Okay. Yeah. So, in Chumash, when it's after man is created, it's described that Yihi ha'adam lenefesh chaya, which Onkelos translates is v'hava ba'adam l'ruach mimalala, right? That people become speaking creatures. So the defining aspect is speaking. Yeah, exactly. No, that is the thing. That being defined. There's significant evidence that our brain capacities for thinking developed simultaneously from our signaling capacity and our communication capacity, and that these were simultaneously derived. There's even a theory of Mercier and Sperber that our reasoning only grew because we wanted to convince each other of things. Okay, and that explains a lot of the strange phenomena that we have of, that have been studied, by Kahneman and Tversky about all of the various human failures we have, systematic failures we have in reasoning, like say availability bias. In order for me to convince you about things, it's good if I could call to your attention something that you're already familiar with as evidence. So they go through many of the discussed examples where it was actually language as being the fundamental goal of, not goal, but whatever to say, the achievement of our brain. And that, it's something to maybe think about. So with such a definition, then instead of being Homo sapiens, we would then be Homo loquens, right? We're the people who speak, okay? And this kind of communication, and if you realize that, if it's coming out of communication, then it also means that when we talk about natural intelligence, we probably shouldn't focus on what individuals are capable of doing, right? We should realize that all of our thinking always used additional tools, okay? So, right, like talking to each other and coming to conclusions that are better than each individual would have come to. Another example is writing. This writing is from Einstein, right? Writing was a very, there's no quiz on this. This is general relativity. But for example, all of us who are mathematicians certainly spend a certain amount of time calculating, and we have pretty weak working memory by just having this little tool of being able to put things on the side and look at it. It makes an enormous difference. And of course, in addition to it helping us do our own thinking, it also is what enables us to pass ideas on to future generations, right? We're not stuck with only what the village elders know, right? I mean, if knowledge is irrelevant in one generation, but it's relevant 2 generations later, the information can still be passed on. Writing wasn't, probably people know, Socrates was very unhappy with writing. He thought that was going to be the end of thinking, right? Okay, similar things in the Talmud. There was the idea that the Torah Shebaal Peh should not be written down. But in fact, I think that the evidence is that writing hasn't killed scholarship. Okay, and it ends up being a tool. So I just want to say that as we're thinking about natural intelligence, we shouldn't think that the basic unit is the person, and the person being restricted to what the brain is capable of doing on its own. Right? Other things we did were we created all sorts of institutions, right? Like universities, laboratories, companies, conferences. All these kind of things are tools that enable us to go much further than we can as individuals. Okay? So let's think a little bit about thinking. Okay? And there are, I believe there are 3 parts of mathematics that are essentially about thinking about things. One area is logic. Okay, and these are pictures of Gödel and Turing. They're not the only logicians, but I had to pick good exemplars, and I didn't have one of Aristotle. And the idea of I think the fundamental idea in mathematical logic is that arguments that convince us are arguments that are made in words, and that therefore you study the syntactic properties of convincing arguments. Okay, and you just think about them as strings of symbols, because after all, if the argument is convincing, it shouldn't be because of who told it to me, and it should be okay for me to get that information in writing as opposed to hearing it orally, right? It's not a matter of, interactive proofs, right? I mean, sort of the classic examples are where we're going to be indicated just by the symbols, okay? And that, and it turns out it's a shocking thing, but that is what the subject tells us, that the mere fact that, that the way I know things about mathematical subjects is due to things that can be done symbolically, that tells me all sorts of things about what we can know in mathematics. And for example, it also implies that there are things we cannot know about mathematical systems, okay? I like this paper, not just because it's mine, but it's a sort of a good example of logic, because when I was working on this, I was working on paper, and I had a slip of the pen, and instead of writing z to the p, I wrote z sub p, and then I realized that's the example, right? So you see, right, that I didn't need the idea of the paper at all, right? I mean, I needed to be able to recognize that, the symbol on the paper was the solution to the problem that I'd been working on, but that, that things could be done by accident. Okay, and this is, of course, everyone's example of, the monkey typing Shakespeare, right? So look, firstly, this idea that it just depends on symbols, that the ideas don't need ideas, right? That ideas are just outputs of symbols, which you then think about and see whether they've, satisfied certain rules, right? That means that in principle, you don't need creativity to be convincing, right? I mean, what you would do is you would just look at, pieces of text, and you would evaluate them and say, are they convincing? Are these reasonable or not? And therefore, this was, in literature, there was Borges' famous library, which was filled up with books, each of which had the same number of pages, the same number of words. Most of them were complete gibberish, but the idea was that all 451-page books, written in English, I assume, were there in the library. So anything that you could learn, is somewhere in the library. So rather than thinking, your job now is to just find it in the library, which unfortunately didn't have a good card catalog. So it was a big disaster. So one thing that this, that this does is it sort of has pushed the idea of creativity in the path, if you worry about creativity, it's not necessarily coming up with the great ideas, it's the idea of the verification is very important. Okay? And mathematics is subject to being able to verify proofs. But I mean, the actual structure, much of what goes on in mathematical logic would be if we had a theory of rationality, where if something was, convincing, then there wouldn't exist an argument that would convince you of the reverse. If you had such a strong theory of rationality, then logic would apply to that as well. Okay, part of the trouble, which we have in a lot of reasoning outside of mathematics is that you can prove something one way, and then you change your perspective, and then you come to different conclusions. Okay, so more suitable to the sciences outside of mathematics that aren't purely deductive areas is the subject of learning theory. This is Vapnik, and I never pronounced Shmuel's name properly, so thank you, Nati. Who are the inventors maybe of statistical learning theory, and Leslie Valiant, who was thinking about the computer science version in a very dominant paradigm. So here the problem is this, right? You're not trying to be convinced, right? The reasoning we're doing is not mathematical reasoning of trying to deduce knowledge from knowledge. But instead, you might be, you're getting some signal from somewhere. You're observing the universe, right? And the goal is, to predict the next thing, okay? And, in statistical learning theory, the observation is that if the thing you're observing is just flips of a coin and it's completely random, you will not succeed in learning it. But suppose that what happened is I flip the coin, and then the next time, I do whatever the coin says to do, and then the next minute I just repeat it a second time, and then I flip the coin again. So there's sort of half an amount of randomness rather than a full amount of randomness, and then you're asking me to do predictions. Can I do better than can I do better than 50%? 50% I would have had been just random. But now I might go ahead and just say, I'll do whatever I did, whatever happened the time before, and that'll be better than random, right? So you begin looking for strategies in statistical learning theory. And in all of these, and the goals of learning theory are not to get the right answer, okay? Because, there's noise. And, things in the real world might depend on, very sensitively on initial conditions, and you might have only observed enough information to tell you about some constant to 5 decimal places, but the thing you're being asked to predict requires 6 decimal places, and so on and so forth. So you have to begin trying to think about the nature of the problems or the prediction problems that you're being asked to solve. Okay, and learning theory, is about how you measure these things, how much is the best you can hope for. And then in the Valiant theory, I sort of like the name that he gives. He says that the goal of learning is to be probably approximately correct. Okay? And that captures sort of, I think, very well what one tries to do in science, right? You want to be probably right. You have no chance of being right all the time, okay? For the reasons that I mentioned. It's only going to be approximate because, the measurements, you never do a measurement that's entirely accurate. You can only hope to do it, up to some approximation. And correct is, well, that's what we want, okay? Right? But it's, of course, very philosophically, learning theory's goal is very philosophically different, I want to emphasize, than the goal in mathematics, okay? And what we do with learning models, of course, so let me, is that, so firstly, the point is that there are theoretical limits to the possible pattern recognition that you can have, right? That's what's measured, like I gave the two different examples of how you're getting a random sequence of heads and tails based on how you make use of what happens on the coin, okay? And, of course, there are real limits to what you can learn in mathematics where you're using deduction, okay? And then, if you're trying to do prediction, and that is where the machine learning has been substantially coming from that tradition, the goal is to be probably approximately correct, okay? And, that's how you would train things. Of course, also once you're dealing with computers, then you're not interested in abstract algorithms that will, to make a prediction, if I need to make a prediction for an event that's going to take place in 20 minutes and, my machine can only do it within a half hour, that's probably not good enough, right? So therefore you begin really caring, in addition to aspects of what are the bounds on your resources. And time is a very important bound. Okay? But there are other resources that you would bound as well. Okay? My daughter told me that this is a creepy picture. And Anat asked me for a picture for the poster about this talk, and I sent this picture, and she also chose not to put it on. But in any case, so this is sort of my conception of sort of what learning theory means for intellectual discussion, prima facie. Okay, right? It's like the conversations you have, at an academic cocktail party, like maybe we'll be having in 40 minutes, right? I mean, you tell things to people about, without absolute expertise. You want to have ideas, and things are going, you're drinking a little bit. That doesn't help humans usually think well. It probably doesn't help computers either to spill fluids, right? And, you get some kind of positive feedback, for some collection of ideas, and you get negative feedback for other collections of ideas. And it's sort of the approval, right? So here the goal, the definition of correct, and probably approximately correct, is that, is that there's some kind of utility function or a loss function, about the predictions, and here it says most of the time they seem to know what they are talking about, right? So probably, approximately, right, the thing that they're saying doesn't have to be actually right, it could be good enough, right? We also observe, I have to say that I have this experience whenever I read popular science, because if it's an area that I know that I don't know anything about, I just love whatever I'm reading. I find it so informative and that I learn so much. But when I read something in an area where I have any expertise, I just notice all the flaws and I think it's absolutely terrible, right? And what's sort of amazing is that as a human, I'm still convinced by the ones where I don't have the expertise. I mean, I just know that I have this built-in flaw that even knowing that I've been convinced so many times of things that the next person tells me and then that person convinces me, even though it's completely contradictory, nevertheless, that's one of my human failures. However, at the, so this is, this is some version about what happens. They're fed texts, and there's some method by which the algorithms evolve. I mean, I'm not going to be talking about the architecture by which this happens. And in the end, some kind of function on input words going to output words is being sculpted by these interactions, and that the hope is, okay, that if most of what they've seen so far is representative of the things that they're going to be asked in the future, then they should do pretty well, okay? Let me point out, that's a rather different than what one does in science. In science, you take the corpus of things that you understand, okay, and then you ask the questions that should be very different than the things that you knew before. You're looking to find where are the breakages in your understanding, okay? However, if your goal is for, say, technological purposes, right, and then, right, I think that that's the field of engineering. The field of engineering is that you try to design your apparatuses so that the known physics will predict exactly how this apparatus will work, and that therefore you make very good predictions and it does exactly what you want it to do. Okay, so this kind of thing, I'm not knocking a subject. I'm just pointing out, where it's coming from and where it could be lacking. So if your goal in science is not just to make predictions, so I have to say this is something that popular science has taken this from quantum mechanics, that you can't understand anything, don't try to understand anything. All that you as a scientist should do is make predictions, and your predictions should be right. In which case, then that would be what learning theory would do. And then you still would have to deal with the problem that you might be asking questions for which the corpus doesn't have the answers yet. Okay? And it's certainly, very suitable for things like where you run Monte Carlos, right, where you run simulations and things like that, right, where again, the situation is very, very complicated and you're trying to guess what's going on. However, for, at least for mathematics, where the goal is to actually be correct rather than approximately correct, there was a feeling that this kind of learning might be difficult. However, the truth is that all of this kind of abstract thinking doesn't go very far because, for example, in the basic model of thinking, say in mathematics that I mentioned, it's the Turing machine, and one has tapes of infinite length, right? One has an infinite amount of memory, okay? And in order to fit, and mathematics is made based on idealizations, and we don't have, and we don't really like saying, oh, but what happens if your tapes are only allowed to be a mile long, only allowed to have, this amount of things. We're going to put in a hard resource bound. It would lead to ugly mathematics, and and no mathematician wants to study ugly mathematics unless they have a very good reason. We'll get back to that later. So the question is, should one think in principle that there's a difference between what humans can do and what machines can do? And so this is stuff that I actually stole from an LLM because like I said, I don't know anything about either humans or machines. But the brain has a very different kind of architecture than a neural net. Neural nets are very linearly ordered. Brain has lots of connections going all over the place. But what's very fundamental is that the way things go along neurons, they're also chemical signals as opposed to electrical ones. And there's a latency time. You can't just immediately go from on to off. After you've done something, you have to wait a little bit. So, if you go down the list, the computers are way more accurate. Brains have a lot of noise in them. They're much, much, much faster. And as you scale up the computers, it's hard to see why brains would do better. Okay? And if there is a reason, it would have to do with the fact that it's a different kind of architecture. And at the moment, we don't have any theory about why one architecture would do better than another architecture. So, so we're not in the situation where we could answer these questions just sitting in an armchair, okay, which is why mathematicians shouldn't really be talking about this. Okay, and that's also comparing the neurons and the speed. So, we're noisier, we're noisier, they're faster, right? Why in the world should we hope to be able to do better? So you would imagine that in the long run, maybe someone would just take some kind of copy of the human brain and just replace every neuron by a wire, okay, and then figure out how to train that. We're not so necessarily so great at training students. Alan's very good at training students. So anyway, conceptually, so the question is, what should we do in the meantime? So this is the first proof project. These are, I'm this guy, and as you can see, the vast majority of the work was done by other people. And I'm not going to report on the whole project, but what we were interested in understanding was the way things are now. In what ways are using LLMs helpful to mathematicians, and in which way is it problematic? Okay, so we did an experiment. Firstly, we got together. My colleagues at Harvard and Stanford were good at contacting the press. Once the press heard about it, then the AI companies decided to take part and respond to this challenge. So what we did was the following. AIs had been very successful in solving problems at the Mathematical Olympiad. They had gotten finally gold medal quality exam papers. But the feeling was that those are artificial questions that people train for, and then they do better, right? Doesn't capture so much the day-to-day enterprise of doing mathematics. So what we all did was we took lemmas or theorems in our forthcoming papers, but papers that we hadn't yet distributed, because once they were distributed, those darn things, they read everything, so, you can't ask it something that you put on the web yesterday. Okay, so we embargoed our work for a while. We asked our collaborators permission to hold up putting out preprints for a while, and the rule was that we didn't want the problems to be too hard, so none of these things had a solution that required more than 5 pages of writing in a way that a mathematician would be able to read and understand and accept. Okay? The problem that I put on had a solution that was 2 pages, in fact. And the goal wasn't to do the hardest parts of math. These were just sort of little pieces of the research project. And, okay, so now let me report on, okay. So here is a report from the web, okay.
AI wouldn't cross anytime soon. It was not language, not creativity. Mathematics, well, that line just broke. Google DeepMind built an AI that independently solved open, PhD-level mathematical problems that human mathematicians have been stuck on for years. It independently explores open problems, reasons over long chains of ideas, abandons dead ends, and produces new. This marks the arrival of mathematical AGI, an intelligence capable of discovering new structure in one of the hardest domains humans have ever created. All right, so Google built an AI research agent called Alethea, and it just independently solved 6 world-class mathematical research problems. And these were open, PhD-level problems from active areas of modern mathematics.
Well, listen, 25 minutes.
As part of something called the First Proof Challenge. This achievement is being described by DeepMind researchers themselves as more significant than winning a gold medal at the International Mathematical Olympiad. That sounds dramatic until you understand what kind of problems these actually were. The International Mathematical Olympiad is about solving extremely hard problems under time pressure, using known techniques in First Proof is different. These problems sit at the research frontier. In some cases, only a few dozen people on Earth fully understand the question. There's no known solution path, no standard toolbox you can apply, and no guarantee a solution even exists. In this challenge, there were 10 problems total. Alethea solved 6 of them, fully, correctly, with 0 human intervention during the solving process, and within the official submission deadline. That alone would be shocking, but the reactions from the mathematics community made it in the field, no other AI system even came close. Aletheia didn't just solve it, it produced a solution so clean that the mathematician who originally proposed the problem personally confirmed the reasoning was correct. And then Terence Tao, widely regarded as one of the greatest living mathematicians, casually said in an interview that AI has become his junior co-author. That one sentence should make you pause. So what exactly is Aletheia doing differently? This isn't a chatbot that happens to know math. Aletheia is a long-horizon research agent built on top of DeepMind's Gemini 3 DeepThink system. It's designed to work on problems that require sustained reasoning over long periods of time, with thousands of failed attempts along the way. DeepMind actually ran 2 versions of Aletheia based on slightly different underlying models and cross-checked their outputs. Together, they solved problems 2, 5, 7, 8, 9, and 10. The remaining 4 problems were not solved, and that detail matters a lot more than it sounds. Most AI systems will happily fabricate something that looks plausible. That's fine for casual use. In mathematics, it's a disaster. A single convincing but wrong proof can waste months of a human expert's time. DeepMind tackled this by designing Aletheia with 2 internal roles that constantly clash with each other. One part acts as a generator, aggressively proposing ideas, strategies, and speculative solution paths. The other part acts as a verifier, whose entire job is to attack those ideas, check every logical step, and reject anything that doesn't hold up perfectly. Inside the system, these 2 are basically arguing nonstop. And here's the key point. When Aletheia couldn't solve a problem, it didn't bluff. For the 4 unsolved problems, it either explicitly reported no solution found or stayed silent when the time limit expired. That restraint is not a limitation. In high-level research, that's a feature. DeepMind even says this directly in the paper. They are willing to sacrifice the ability to solve some problems if that's the price of never producing nonsense. Now, let's zoom in on problem 7, because this is where things get genuinely uncomfortable. Problem 7 sits at the intersection of algebraic topology and differential geometry. In simplified terms, it asks whether a certain kind of discrete group can appear as the fundamental group of a compact, boundaryless manifold under strict conditions on its universal cover. That sentence alone filters out almost everyone. And the answer is no in 2 completely different ways. The first proof is almost shocking in its simplicity. Using the assumption that the universal cover...
Okay, I think I'll stop it there. Okay. I'd like to react to this a little bit. First of all, I'm responsible for problem 7. I don't think it's really that esoteric. Yesterday I explained to people why it might be an interesting question. The truth is that it had been an open question for a while. A student of mine had done every case of this except for one leftover case. And then that problem was sort of ignored for a while. Then about 15 years later, me, my thesis advisor, and another one of my students got together for coffee. We discovered a proof after a few hours of pleasant conversation. And as I said, the proof only took a couple of pages. But I still think it's a publishable paper, it's interesting, etc. I think that there are a lot of things they get right. That it's extremely bad when things look convincing and are wrong. Okay? And, however, they're...
Rationally acyclic.
I was going to go back. And it is true that, many AI, we examined many LLM-produced solutions to these problems, and including ones where I have evidence that, mathematicians were involved in interacting with the AIs. And they all failed for 1 or 2 reasons. They looked really, really beautiful. If you didn't have subject knowledge, it could have easily taken many hours to find the errors. But it turns out that there were just 2 characteristic error pitfalls that they all fell into as being natural pitfalls. So in fact, on the first proof page, we explained these pitfalls because that was what all of them had fallen into, except for Aletheia. Aletheia did have two agents, okay? I'm not going to go back to show where they had their internal report card. Unlike this, this video, actually one of the agents also fell into the pitfall that the other LLMs fell into. It isn't, they describe that there are sort of two solutions, and one of them implies really much stronger things. Well, those much stronger things are in fact false and already in the literature as being false, and those were the ones that other companies also fell for. So none of them are really very good at removing errors. I mean, Aletheia, though, is very, and I'll say a little bit about Aletheia's proof, which was also interesting. But let me just say something about another one of the companies. One of the mathematicians working at that company. So, by the way, so in order we put these problems up, and we also, when we published the problems, we also encrypted our solutions so that when a week later the thing was over, people would be able to. We published the key, and then people would be able to read our solutions and see that we had them at the time that we asked it, that there was nothing funny. We weren't, trying to get free AI technology or anything like that. So one of the companies that had published here, the statement is that those things don't exist. They had actually claimed the construction of one of these things. So that one was novel. It was a different pitfall than the other ones, and it took me about 15 minutes, and I was nervous. Oh, maybe my proof is wrong. It was going to be so embarrassing. So I'm kind of relieved that, well, I'll tell you about the Aletheia solution in a minute. But yeah, so the guy at that company told me that, by the way, we had 12 agents working on it, and we had a whole range of solutions. Some of which were these counterexamples, some of which were proofs. And I said, it would have been really good for you to have published, all of the things that came out. It would have really helped our scientific project. And they said, no, we couldn't do that, because then we would be publishing something that we knew to be wrong. So that's kind of a little bit of a problem here. And I mean, as you could see, various things aren't being represented completely well. In the internal report card that they showed, they do show that one of their, agent number 1 on problem 7 actually did it incorrectly. I mean, but the movie said that it did it correctly and that it had so many more implications than the problem had originally asked for. So there, it's clear there's sort of there's a lot of interest and a lot of attention being paid, and that therefore many of the claims that one hears need to be taken with a grain of salt. On the other hand, I was very impressed by what agent number 2 did by Aletheia. The proof had 3 different steps, which were just like the proof that Capel and Yan and I had, and 2 of the steps were done by mathematical, they were done in different words. We used algebraic methods, they used analytic methods, but there are but it's known what are the analogies between those subjects, so they were completely analogous solutions. And then the third part, they did by a method that was, really kind of quirky, and it didn't, it doesn't generalize as well as the method that we came up with. But I still found it really impressive. I didn't notice that there was this quirky approach to it. Okay, if I now turn this into a math lecture, I'd be much more likely to explain their method than mine. Okay, it is somewhat more elementary. Now let me go back to my talk. So what happened with that company? So they had this dozen things, and they couldn't publish the wrong one. That they knew to be wrong. So then they asked their internal experts to look at these dozen to decide which one to prove, which one to publish. And they thought that the one that was a counterexample was more plausible than the one they said, oh, well, than mine. They said that they came up with my proof, so therefore, my proof looked less convincing. In other words, at the cocktail party level of discussion, right? So if you're not an expertise in that specific area, and you're using this to help you, okay, there's a real risk that the LLM will convince you of something that's wrong. Okay? So our need for, for critical thinking, is zooming up. I mean, every mathematician needs critical thinking. Every person, every citizen needs critical thinking. But in the world of LLMs, no. Now, how am I going to find this again? No. I apologize for this computer failure.
Ask Gemini.
Oh gosh. No, where is it? Okay.
Someone with good Apple technical.
Yeah, can anyone help me?
Maybe we want to open Pascal at the Safari. Try command double.
I don't know where it is. Oh, can we first get this?
Yeah, these guys will say something.
Yeah, you'll help me?
I don't know try. I don't know enough. We're mathematicians, not computers.
Yeah.
This is tough.
Yeah.
They don't have it.
Oh, wait a second, let me, no.
Maybe you want to open it from the email.
Yeah, there we go.
Okay.
What about this password?
Okay.
And now do control L? Yeah.
Okay. Okay, now reviewing everything. Okay, creepy picture. Okay. Yeah, so, subsequent to first proof, there was a very impressive piece of work done by OpenAI, the unit distance conjecture, this is a very beautiful piece of mathematics, and it applies number theory, Golod-Shafarevich towers to a problem in combinatorial geometry. Not a completely unprecedented idea. I think Noga had the idea that high-dimensional fields could be relevant to the problem, etc. But this is the kind of problem, it was using bridges between areas, using known technology, though in one area, but it was very delicate. It was a delicate argument. And even if you had expertise and thought to use it, humans, would be maybe something that doesn't speak to our strengths. So one of the failures is that not so many people think about combinatorial geometry and think about number theory. Okay? Now many of the people understand that they should be thinking about both at the same time. But another thing is that you have the idea to do this, but then to do it is a very delicate kind of thing to do. And if human who has to do something delicate and the first 15 things you try don't work and none of them are looking like they're making progress, people give up. Okay? So we have a bunch of, right, I don't want to say that this is a sign of our weakness, but there are things, it's clear that LLMs are doing something differently than we're doing. Okay? And by the way, if there had been LLMs and then someone had the idea, oh, let's create some Homo sapiens, and they say, what's the use of that? They say, oh, but they're so energy efficient. We don't need, and also they learn from so many fewer examples. You don't have to train them on the whole corpus of human knowledge, right? In order for them to, tell you which restaurant to go to. Right? It's clear that we're doing things differently, right? And, and neural nets, before they got to a certain size, the outputs didn't seem particularly impressive. Okay? So, a model that I would like to suggest is that there are, we humans have limitations. We don't have Turing tapes that are 1,000,000 miles long, right? There's the 5+or-2 paper, right, about how much short-term memory and working memory that humans have. It seems that Our brains, though, are able to handle more inputs than our conscious mind is able to handle. I wonder whether that's why so many of us have our best ideas when we wake up in the morning after having obsessed about a problem as we fell asleep. But speculative. But we clearly have weaknesses, some of which have been identified, some of which we haven't. And if there would be a device, which for some reason we don't understand, but it doesn't have some of our weaknesses. Maybe it doesn't have all of our skills, okay? But the problems that we're stuck on because of our human weaknesses, because we can't think about 7 things at the same time, right? Those would be the things where you would expect there to be some kinds of solutions. Okay. Okay. I've already been pontificating about the lessons. Yeah. So this is a cover from Nature about a phenomenon. This is partially the fact that LLMs hallucinate. They give you a lot of stuff. This is about a thing called model collapse, which is that when LLMs are trained on the outputs of other LLMs, and you iterate a few times, then they ultimately produce complete gibberish. Okay? I'm not sure that isn't true of humans as well. Okay? No, when I first heard it, I thought this was an LLM phenomenon, but given that my theme is that I can't, at my level of understanding, I can't conceptually distinguish, but that's, if you think about it, we've developed technology to advance in math and science. Science, right, we have the repeatable experiment. We have journals. We have very tough refereeing, right? We don't just go ahead and take the output of our cocktail conversations and build on that, right? If you have this kind of echo chamber where people with one set of interests, produce knowledge, and that's how they go ahead and train the next conversation and so on and so forth, it doesn't seem to be working so well for humans and society either. But I do think that the architecture of LLMs does have some kind of trade-off that requires hallucination to exist. But hallucination, we shouldn't think so little of it. I mean, hallucination might just be the other side of the coin for imagination. But you then really need some mechanisms for solving the problems. This picture has nothing to do with the writing underneath. So the writing underneath is, for math, there is a solution. Remember, we had that robot with checking out the output of the monkeys, right? I mean, we could go ahead and try to check, as rigorously as we can, the output. We might get AIs to assist us in tearing apart each other's work, and so on. There is a formalization project, which generically goes under the name Lean. I think that this is really valuable. I have to say that one of the reasons that companies are so interested in math is not really because they're so interested in math. I don't think. It could be. But I think part of it is because in math you can tell if something is a hallucination. There is a ground truth that you don't have to fight about. So I think that this is really wonderful. If they do this, it will really make mathematicians happy. But this is precisely something. We don't have arbiters of deciding whether something is a rational argument that would apply to outside of mathematics. So to the extent that the LLM companies begin trying to do math more the way mathematicians do, it might not help them so much in their broader goals. Oh, now the other thing is...
That's also why they like games.
Yeah, right. Well, for games you could also be competing with other people, right? I mean, and
And also there's a clear goal.
and there are clear goals, yes. Okay. What?
There's a ground truth who won.
Right, and also what the score is, etc. Right? I mean, so this is Murray Gell-Mann, who is famously quoted. I don't know whether he actually said this, but he said, "If I've seen further than other people, it's because I'm surrounded by midgets." Right, which is of course a takeoff on Newton. So that's a little bit about my take. I think that when we think about why we work on math problems, there are various reasons. Okay, some problems are suggested to us by physics, by other areas of intellect. Right? There's utility. Okay, there are other problems where we're which are motivated by the internal dynamic of mathematics and a search for beauty. Okay, but we're not looking for problems because they're hard. Okay, so PhD level problems, etc. It's not that we're going ahead and giving each other exams all the time, trying to say, oh, can I do this? Really, can you do this really, really hard thing? I know how to do it. I did it last night. There might be such examples, but it's not the generic situation. Really, what happens is that we're interested in problems because for some reason or other they're interesting. Okay, and now the reason that the problems are hard is because the interesting, easy problems get solved right away. Right? So if something has been interesting for centuries, and it's still open now, it's probably a hard problem. Now, if till this point in time it's been humans who've been mainly thinking about problems, you can ask, why is it that it was so hard? So now it could, there are various problems that get solved in various ways. Okay, like I said, I don't think we understand thinking well enough to understand how all problems are being solved. Some problems, it could just be that the complexity, that you need to keep 6 things in mind at once, or you need to do, hundreds of pages of calculations before you can see that something is promising, or, that there's some method to do it, right? So problems of that sort could be open, interesting, and solvable because the things that we're bumping up against are the things that we haven't modeled, which is what's exactly the implications of some bound on a resource that we happen to have. Okay? And, so I think that, one could expect, now that there's a tool that doesn't have some of our weaknesses, we should expect many old problems to be solved. And I think that that's something to be applauded, and it's something that I think that we all should want to do, to make use of. I talk to LLMs all the time. I have to say that almost every conversation ends in tears because, more or less, I guess I'm not tolerant enough of the hallucinations. But anyway, I think, but this, does pose problems. This is something from the first proof project, our paper that we produced. We wanted to emphasize that mathematics isn't merely this business about solving problems, proving theorems. There are sort of many other aspects. There's conjecture, about speculating about the existence of, of structures behind things. We make long programs and strategies. Right? There are many things that we haven't yet seen the LLMs do, although we've seen them, on some kind of smaller situations. And again, I haven't, gone through. It's really interesting to try to read through the 120-some pages, where, in the solution to the unit distance problem. The final solution is only 20 pages long, but there's about 120 pages where it describes what its thought process is as it's going on. And, it's something to understand. But we look for new concepts. And, and that is something that so far there has been no evidence of. And I'm wondering whether actually LLMs would be coming up with new concepts. The following argument might suggest otherwise, which is this. I keep coming back to our very small working memory. So how do we get around that, right? So if I have to remember, a phone number might be 7 digits long, so then I might say, oh, the last 4 digits are 2024 instead of 2024, so then it's a smaller number of numbers, right? So what happens is that a lot of times we create concepts that will help us, and that the chunks are smaller so that we could keep things in our minds. If and we create lemmas and theorems so that they could be cited and pulled rather than having to repeat this in the course of a proof. If something was capable of producing proofs willy-nilly with no effort at all, it wouldn't need the memory of, proofs that have been done before, right? I mean, it might need to communicate that, but then it would be, coming up. So I'm wondering, if one of the things it does is, it keeps track of more things than we can. It isn't natural. It won't have the same pressure to be creating concepts. Which I think for working mathematicians, the conceptual frameworks in which mathematics is embedded are to us, into human mathematics, I think a very central aspect. And so predictions. So predicting, that's Yogi Berra. It's very hard, especially about the future. One thing is, not just machines suffer from model collapse. People do. This is a serious problem in math journals already. Papers are very technical, very hard. It's very difficult to get referees. And after a referee has held a paper for 2 years, they haven't been working on it 2 years, I know. But then they write the report in 1 week, and they only pretend to have read it. I don't know. It's a problem. And given the fact that that there are options like lean, which don't solve the problems outside of mathematics, but within mathematics, I think that would be, very advantageous. And I believe that in the future, mathematicians will be pushed to present their proofs in machine verifiable ways. And that if you don't, it'll be said that, you're just giving a heuristic argument. And things like that have happened in the past, like the introduction of epsilons and deltas into analysis. Or schemes into algebraic geometry, where much of the writing of earlier generations, wasn't viewed as readable anymore. But one should expect that many old conjectures to be solved either by the LLMs or by hybrids of humans and LLMs, if what's missing still requires whatever it is that humans give that LLMs don't. Yeah, so let me just say, there have been a number of occasions in my career where I'm working on a problem, but I don't just work on one problem. I work on a whole cloud of problems, all of which, there may be even in different areas of math, but I feel that they're all governed by the same central obstacle. And that, and the fact that they're in different areas is advantageous because each one suggests different kinds of ideas. And you just figure that because of the analogies, you'll be able to export things once it finally cracks somewhere. And so you think you're going to solve 5 problems when you solve one. And you solve one and you're very, very happy. You celebrate because you now know you're going to solve 5, but you only solve 3 of them. Because after the fact, despite all of the success and that you did make a genuine breakthrough, you don't understand things well enough to solve all 5. There was this obstacle that was analogous, but understanding that obstacle wasn't enough. Okay? So that's sort of what I feel. We don't have a principled understanding about why LLMs do as well as they do. We have nothing, of an understanding about how it is that humans do what we do, right? I don't think that there's any evidence that, sort of all the problems of human thought, until we go ahead and do better ones like Xeroxing the brain and putting it into silicon, should be able to do better. But anyway, so there are many, let me just finish, there are many challenges, not just for math. Economics, it's really a problem about, entry-level jobs. Many people are losing jobs, I think, in many cases to LLMs who haven't been able to show that they can do it better. I think that, they can do it cheaper, and in some case with a worse product, but the difference in value in the product doesn't justify a salary, right? But it becomes, one doesn't, there are big problems, widening income inequalities, educational. I think that if things, students, are under a lot of pressure, and it's very hard, I told my undergraduates, you could do your homework by using AI and you'll do faster, but if you don't understand what's going, the concepts, then you're not going to understand when they're giving you the wrong answers. Okay, but when they get better and they only give right answers, then the students will be missing the opportunity to learn. And figuring out how to teach in this environment, I think, is going to be quite hard. I think I've used up my time, so I won't discuss any more of this. This is an AI-generated slide of what it thinks the problems confronting society are that it's producing for us. And I thank you for your attention.